Hey everybody. Hope you're well this morning. Hope you're doing all right. Today we're going to be looking at explaining a few things. Okay, and I don't mean that in the sense of kind of going back and going, okay, this is what we did last time. This is what we did last time. This is what we've done before, and that kind of thing. What I mean by explaining some things is explaining why some of the things we've done before are things that we've just said because it is. Okay. We're going to be looking at two different things in the next couple of videos. One of them is called the chain rule, what we're looking at today. And the other one is going to be reverse chain rule or integration by substitution. Okay. It's a shame that differentiation by substitution isn't called what it is, in my opinion, because then it would be kind of a little bit more obvious as to what it meant. Because some of the other rules that we have to do with differentiation, they actually spell out what they mean, but the chain rule kind of doesn't. So we're going to take a look at the chain rule in this video, and then we're going to see just about how we do in terms of this before thinking about maybe going on to looking at integration by substitution later on. Okay, so hope you've got some pen and paper ready so you can follow some of the things as we go, and let's get started. So what the chain rule does is it allows us to take functions which look complicated or are perhaps a makeup of two functions merged together a little bit to create to differentiate it, okay? And the example that we've got here is kind of a function within a function, which is its primary, it's its main use. That's what it's used for, okay? So what we want to do is we want to be able to differentiate stuff like this because composite functions happen quite a bit. Now, if we look at this, using the tools that we've got at the moment, there's no way for us to differentiate this as it is. Okay. But what we're going to do is we're going to think of this as differentiating by substitution. Okay. Now, in my head, if I'm looking at this thing would be a whole lot easier if it was just like u to the power of 5, wouldn't it? Like if instead of this bracket wasn't there and instead it was just this letter u. That would make it a lot easier because we know how to differentiate u like that. Okay, we would know how to differentiate that. Only instead of finding dy by dx, I would be finding dy by du. Okay, so for this, I'd be rewriting it as u to the power of 5. And what we're going to say where u is equal to 3x to the power of 4 plus x, that bit was inside of the brackets. Okay. Now what we're going to do here is we're going to find dy by du. Well, that's just going to be 5u to the power of 4 just by differentiating normally. Okay. But we're not trying to find dy by du, we're trying to find du by dx, okay? And that's where we do something a little bit interesting. What we're going to do here is we're going to multiply by du by dx on both sides. So we're going to find dy by du, which we've just done, and then times by du by dx. Okay. Now, if you're looking at that and going, well, why are we timesing by du by dx? What? Take a look at the fraction. This isn't a proof, but it's a good kind of indicator as to why we're doing what we're doing. We're trying to find dy by dx. Now, take a look at what's on the numerator and the denominator for each of the fractions here. On the numerator for this fraction, we got du. On the denominator for this fraction, we have du. What that will kind of do in inverted commas, it's not a proof, but it's kind of giving us an indication, is it's going to cancel those two things out to get us dy by dx. Okay, it's not a proof, okay, but it is what we're going to look to do. Okay, what I'm actually going to do is I'm going to do that du by dx in a different color just to make it stand out that little bit more. So we're going to do du by dx. So the dy by du, we've done that. That's just 5u to the power of 4. And now we're going to times by du by dx. Now, du by dx, that's going to be equal to, well, we're just going to differentiate this normally. So we're going to have 3 times 4, which is 12, x to the power of 3 plus 1. Okay, so I'm going to have 5u to the power of 4 times 12x cubed plus 1. Imagine putting that in brackets just to make it that little bit tidier. Okay, there we go. So what that actually is working out, what we've actually got there to finish with, is dy by dx. Okay, so what the chain rule does is allow us to differentiate functions of functions, and what it is what I've just bubbled in that little black bubble there. Okay, to find dy by dx, we would work out dy by du by making a substitution, and then times by du by dx. Okay, the substitution differentiated. Now, if I'm honest, I don't go through that whole process every time right now when I do when I use the chain rule. I tend to think of things like as a kind of a part of a bigger picture. But if you're starting out with the chain rule for the first time, I do encourage you to think of, okay, what's the substitution we're going to make? And it typically is the thing that would make the function considerably easier to work with. Okay, you can see that here I made this substitution just so that it meant a letter to the power of something. Okay, it could be that if you're differentiating a trig function, that you make the thing that is inside the brackets your substitution, because then it would make it much easier. Okay. So yeah, that is the kind of the core use of the chain rule. This is kind of like what it does in general. All right. Just so that you can have a go at using it like we have here for yourself, I would like you to have a go at the following one, just to see if you can do it as well. We're going to have 2x cubed plus x squared to the power of 6. Okay. What I'm going to do as well is just put up a quick little timer, maybe for just 2 minutes, just so that you can have a quick go of that for yourself. Okay. Counting down for 2 minutes. Here we go. Remember, if you get questions when doing some of these exercises and you want to email them out to me so that you can ask them, please make sure that you do. Okay, make sure you get answers to the questions that you have. All right, so let's put an answer together for this one so then we can see how that went. So I'm going to use two different colors just to split up what I've got. I'm going to let u be 2x cubed plus x squared. So then du by dx is going to be 6x squared plus 2x. Okay. And so then we're going to have dy by dx is equal to dy by du times du by dx. Okay. I did say I was going to use different colors, so I shall. And so now I need to think dy by du. Okay, so this thing, which I've got here at the moment, that would become us saying u to the power of 6, because we're going to make the thing inside the bracket the substitution. Okay, so dy by du, so this function here, differentiated, gives us 6u to the power of 5. Okay, and then we're going to multiply by du by dx. Okay, so that's going to be multiplying by 6x squared plus 2x. Now, I just realized that there was something that I didn't do for both of these examples. Okay, what we should do, and what I didn't do, was to put the substitution that we made back into our answer. So for this one, what I should do at the very end is to put our substitution for u back in to the answer that we got so far. Okay, and I should do that up here as well. So I should have 5 lots of 3x to the power of 4 plus x times 12x cubed plus 1. Okay, I should do that, and I've missed my power. Okay, it's early in the morning. Power of 5. There we go. So that's how we use the chain rule. Okay, but we don't want to be able to just use it with functions like this. We want to be able to use it with a range of different functions. Okay, and as we kind of go through the next few examples and maybe try a few out for ourselves, we're going to see if we can find a way of shortcutting this method so we're not having to write du by dx, let u equal this, and then everything out over and over again. Okay, so we're going to look over the course of the next couple of slides just to shortcut this method a little bit so that we fully understand it. Okay, so let's have a look at doing that. Okay. So in order to shortcut this a little bit, what we're going to do is we're going to think about this as two parts. Okay. We're going to think of things in terms of an outer function, the kind of the bigger picture, and the inner function, the thing that would normally be our substitution. Okay. And the reason why we're going to split it up into these two things is because these two things are what would make up the chain rule or the differentiation by substitution. Okay. So the outer function differentiated, that's going to be our dy by du. And the inner function differentiated is going to be like us thinking of the du by dx. Okay. So taking a look at this one, the outer function for this first part is the bracketed bit to the power of 3. Okay, it's just something to the power of 3. Okay. So if I were to differentiate something to the power of 3, what would you get? Well, if I was to differentiate something to the power of 3, I would get the power coming down to the front. The power decreases by 1. So I'd get 3 lots of something to the power of 2. Okay, so that would be what my outer function would be, what my dy by du would be. My inner function would then just be the bracket differentiated. Okay, so this would be 2x. The 1 disappears because it's a constant. When you differentiate a constant, you get 0. Okay, so thinking about it in terms of an outer function and an inner function will help speed it up so that you're not thinking as much about what substitutions you're going to have to make. And that's a good thing. Okay, so let's see if we can use this idea of the outer function differentiated and an inner function differentiated to help us with some of these. Okay, so the next one, similar setup in terms of the bracket, which has got something different inside of the bracket. So the outer function again is something cubed. So if I were to differentiate something cubed, what would I get? Well, just like we had on the last one, we'd get 3 lots of the something squared. But now we multiply by the inner bracket, the inner function, differentiated. And if you differentiate a ln, you get 1 over x. Okay? And remember that in the long run, the method that we're doing in our head is creating a substitution, differentiating the substitution, and then putting things back. Okay? That is what we're doing on the long run. We're just looking to shortcut some of those steps. Okay? Now, what I'd like you to have a go at, I'd like you to have a go at this third one yourself, just for 2 minutes, just to see how you do with this third one. Okay? And oh, hello. That's interesting. There we go. It's back. So 2 minutes. See how you do with this one. I'm possibly thinking is 2 minutes too long, but we'll stick with 2 minutes, okay? If you're done with this third one, feel free to have a go at the fourth and fifth one as well, ahead of time, so that you're continuing to challenge yourself where you can. Okay, so here we don't have an obvious bracket that we want to... Wait a minute. We don't have an obvious bracket that we want to use to make a substitution or to kind of call our inner function. But what we do know is that if we were to differentiate e to the x, that is really easy. Okay, that's just e to the x. So what we want to be able to do then is if we were to say, okay, what about if we made that bit our inner function? Okay, so instead of it being e to the x, it becomes e to the u. Okay, so here our outer function is going to be e to the h. Okay, so if I differentiate e to the h, I get e to the h. Okay, so that bit stays the same. Kind of makes sense because we've said with exponentials that the rate of change is proportional to the amount of what you've got at any one point. Okay, but multiplied by the power, in this case, the thing that we made as our substitution, differentiated, is 2x plus 1. Okay, now this is where it's worth making a note. We said that if we differentiated a exponential function, so if we did d by dx of e to the f of x, we said that it would be equal to f primed of x e to the f of x. Okay, that's what we said. We said this in a previous video. Have a look at the structure that we've got here. Okay, we've got e to the f of x, e to the power of our function, which is what we started with, and a multiple of the derivative of that function. Okay, so the rule that we learned earlier, the general rule that we learnt for exponentials and logarithms, is actually using the chain rule. Okay, so this we should hopefully recognize a little bit. Okay, so this is actually using the chain rule in disguise. Okay, but we'll look to get a move on because time is ticking along. 2 to the power of x plus 1 squared. Now, this kind of a thing we looked at when we were doing logarithms. Okay, we said that if we had an a to the power of x, that differentiates to a to the power of x times some other term, which I'm trying to hope that you remember. Okay, so let's deal with the outer function first. It's just h squared. So if I differentiate h squared, I get 2 h to the power of 1. The question is, what does the inner function, that bracket, differentiate to? Well, the 1 will disappear, it won't become anything. So differentiating 2 to the power of x, what we get is 2 to the power of x times by that constant term that we get from having a different base, which is ln of that number. Okay. Differentiating a to the power of x, that is one thing which I remember a comment, someone saying that they like to ask about that because it's something that people often forget about. Okay, so just remember that this will differentiate to a to the power of x ln a. And one more for this page. Ln of sine x. Okay, outer function. I want you to follow with me on this one. So outer function, differentiate it. Write it down. Inner function, differentiate it. Write it down. Now, if you got 1 over sine x times cos x, you're good to go. if you wrote 1 over x times cos x, remember that whatever's in that bracket sticks with that outer function differentiated, okay? So that sine x should stick with the outer function differentiated. It becomes 1 over sine x. This is the kind of scenario, possibly, where if someone was not sure how to differentiate it, I'd say go back to your kind of steps, like your first steps that we made with the chain rule. Okay, let u equal sine x. So du by dx is cos x. Okay, so dy by du is 1 over x. Okay, so putting our answer together, dy by dx, oh sorry, that should be 1 over u. There we go. So that means that dy by dx will equal 1 over u, which is 1 over sine x, times cos x. Okay. Now, in future units, you'll have a way of simplifying that, but at the moment, we don't, so don't worry about it. Okay. And I've just realised that the timer is covering all of what I've just written, but now it's not. Okay. Okay. So, that's a little bit more practice, okay, from differentiating things which would use some kind of a substitution, or what we're going to refer to from now on as the chain rule. What we're going to have a look at now is I'm going to go through maybe, we've got a slide of further examples and things like that, but because I don't want this video to become too long, what I'm going to do is I'm going to set the, I'm going to do a couple of them and then ask you to have a go at some of them yourself, okay? So the ones that I'm going to have a go at, where's my pen gone? There it is. Okay, the ones that I'm going to do are, I'm going to do this one, okay, and I'm going to do this one, okay. So I'm going to do the ones which involve trig, because we've not seen much trig yet, okay. The other 3 are ones that I'm going to want you to have a go at once I've had a go at these 2, okay. And I'm not going to write anything, we're just going to talk our way through them, okay. With trig, you have to be careful to see if there's any powers involved, okay. This top one, there isn't any power involved, okay. So this is effectively just going to be sine 5x. When there are powers involved, we have to bear in mind how the powers are written in terms of trigonometry. When we're talking about sine squared x, what we actually mean is sine x all squared. Okay? The sine squared x is a shorthand that means sine x all squared. Okay? And when we get into thinking about some of the integration and differentiation that we'll need to do as a part of further maths, the distinction is important, okay? And also thinking about the function that you've got, but we'll get onto that at a different point, okay? For the moment, we just need to know that sine squared x actually means sine x all squared, okay? Now, differentiating that is much more like some of the stuff that we had on the previous slide. Okay, so we've got the outer function, which is squared. So that would be 2 to the power of 1, okay, which is just 2 sine x. But now we need to differentiate the thing that's inside of the bracket. Okay, and if we differentiate sine, we get, hold on, pause. Okay, so from differentiating sine squared x, or sine x all squared, we get 2 sine x cos x. Now, the other one which I wanted to have a look at, which was this fourth one, okay? So we're going to have to think how to write this one again. Cos cubed 2x, just like we had this here, means cos 2x all cubed, okay? That's what that actually means, okay? Why we don't just write that, personally, I have no idea. But apparently this is the notation that we've, as mathematicians, decided to work with, okay? So, outer function to the power of 3. That would become 3 to the power of 2. Differentiate cos 2x. Now, if you wanted to, you could see this as another use of the chain rule. Or you could just remember what we'd said when we were looking at differentiate trig functions before. Okay? Because cos 2x, and draw a little arrow over to here, that is the same as thinking cos 2x like that. And you could use the chain rule again. In which case you'd get 2 lots of, because 2x differentiated is just 2, 2 lots of cos differentiates to negative sine. Okay? I'm just going to write in what I was saying there. So to d by dx of cos 2x, we could use chain rule again. Okay, so there are 3 here, okay, and I'm going to say that roughly 5 minutes, okay, just to see how you do with those 3, okay, and when we've had a go at those 3, we will see how we've done. And always, if you have questions, write them down so that you can email them to me or discuss them when we get back into college. If you want to get answers to them sooner rather than later, feel free to email them to me. I'll give you some answers to them to the best that I can. Hopefully everyone's doing all right with these. Hopefully the first one and the middle one at least hopefully aren't causing you too many problems. But hopefully that last one is giving you a little bit of thought as to what you should look to do. We'll keep going for the 1 minute and so, but after this, there's not much left to this video. I'm going to put up a couple of problems up screen, but then tell you that if you want to have a go at these problems, to pause the video and have a go at them for you yourself. All right, so there's our time. So we've got these last few remaining questions to have a quick click through, and then we will go from there. So outer function is a sine of something. Sine differentiates to cos, so we're going to get cos of something. The something differentiated, well, 5x just becomes 5. So 5 cos 5x. The middle one, we've got a radical, a square root sign. Okay, so how would we rewrite that? Well, a square root is the same as something to the power of a half. Okay, so now we've got something which we can differentiate. We've got something to the power of a half. Well, that would become half something to the power of negative a half. Differentiate the something. In this case, we just get 1. Okay. Not particularly interesting derivative, but it's still one that's important. This last one, e to the x. Okay. So e to the x. The function is that the function that is the thing that we're going to have to... hang on, let me start that again. The function that we're going to have to consider as our substitution is e to the x. So I've got e to the something, which differentiates just to be e to the something, function that we started with, times by e to the x differentiated, which is just e to the x. So e to the x differentiated is just e to the x times e to the x, which is quite an interesting tongue twister to get your tongue around. E to the x is e to the x times e to the x. Quite fun. Anyway, I'm wittering. Hopefully those you've kind of managed to be able to take yourself through now. We've kind of got 40 minutes into this video at this point, and we've gone from thinking of differentiation by substitution, okay, and started to think of it in terms of looking to speed things up by thinking of it in terms of an outer function and an inner function, to now kind of hopefully being that little bit more fluent with the chain rule as a whole, okay? So time now is to try and test yourself with it, okay? Here are 2 questions which I'd like you to have a go at, but I'm not going to set a countdown timer going. I'm just going to say if you want to have a go at these questions, pause the video and then go from there. But before you do, can you, if possible, just think to yourself, where are you on a scale of understanding right now? Are you a 1? Are you super up there? Are you kind of going all guns blazing at this point? Or are you further down that scale? Are you kind of not so sure of where you are? Maybe ranging down to about ranging down to 4. Okay. And feel free to type numbers into the chat if you want. Just think to yourself, okay, where are you at the moment? What questions do you have? Okay. So, if that's all said and done, feel free to have a go at these questions. Pause the video right now. Hopefully you've paused the video, because if you haven't and you don't want to see these answers, you need to pause it real quick, because the answers are coming up now. Okay? So, for this first one, just thinking about, for the first one, we're just thinking about differentiating a log. Okay, we have the differentiated function over the original function, which is the general form that we saw when we were looking at logarithms before. And we've got that for the second one, we need to rewrite the square root as a power of a half, differentiate everything, and then use the coordinate that we've got to find the value of dy by dx. Okay? What I'll do then is I'll leave this video here, and I'll give you time to process it. Okay? There is a worksheet that I sent out with this kind of work for this week, which is the one that is on the screen here. And this contains just practice on using the chain rule. Okay? You can find this on Physics Maths Tutor by looking for C3 differentiation worksheet C. Okay, that's the worksheet that you'd be looking for if you wanted to have a go at some of these, like some of the extra questions involved. Okay, I think navigating through Physics and Maths Tutor is relatively straightforward. These are the Solomon worksheets. If you're interested, these are the Solomon worksheets. They work for the old spec, but in terms of getting used to some stuff, they're actually pretty good, I think. Okay, so anyway, I'm going to leave it there. I think that's the third time I've said that now, and I actually am going to leave it there. Okay, so thanks for watching. If you enjoyed it, good. If you learned something, even better. All right, I will see you hopefully very shortly in another video.